Let's introduce linear estimation. So recall in the previous video, we introduced this scalar estimation framework. Okay, so it was pretty simple. We had an unobserved random variable, we called that x, and an observed random variable that we called y. And we had to come up with an estimation rule, x hat of y, which was a function that predicted the value of x using only the value of y. And the average quality of our prediction we measured using something called the mean squared error. All right, that's just x minus the prediction squared, take the average. So we know the optimal performance for this kind of criterion is given by the minimum mean square error, or Mmsc estimator. And we learned that that just corresponds to the conditional expectation. So just take E of x given y as your estimator, that'll give you the best performance. Unfortunately, it's pretty challenging in general to work this out, even in the scalar case. So that could just be because the integrals are hard to work out analytically. In practice, it can be hard to collect enough data. And what we want to know in this video is, can we come up with the best possible linear estimator of the form ay plus b for x and get around some of these issues? And that is what we're going to call the linear least squares error, or LLSE estimator, x hat LLSE. That gets the smallest possible mean squared error among all linear estimators. And to put this in context, you can think that the Mmsc estimator that we had, the conditional expectation, that's the best performance among all non-linear estimators. So it's allowed to be linear, but it could also be nonlinear. This estimator must be linear. It has to be just a line with an offset. Okay, so the form of it is just the mean of x plus rho sigma x over sigma y, y minus its mean. Alternatively, you could just write this factor as covariance xy over variance of y. So we know also we can use this formula to get the mean squared error of the LLSE estimator very quickly. So we just write the variance of x times 1 minus rho squared, or variance of x minus covariance of xy squared over variance of y. Those are the same thing. These formulas might be familiar to you as the conditional expectation and conditional variance of a jointly Gaussian pair. And that's because for jointly Gaussian random variables, the Mmsc and LLSE estimators are the same. And that's because jointly Gaussians are nice in the sense that many of the things that you're interested in that context end up being linear, okay? But these estimators apply generally. You can use them on non-Gaussian data and random variables, but they may not be the optimal thing to do. In Gaussians, they are the optimal choice. So the other reason we prefer this is that in practice, it's often easier to work out what this estimator is because we only need to collect first and second order statistics. So by that, I mean the sample mean, the sample variance, and the sample covariance. And we'll see a bit more about that soon. Let's think about some of the basic properties just to have an overview. We won't really need these, but the first is that the estimator is unbiased. So if you take its average, you'll get the mean of x. Why is that true? Well, just by linearity of expectation, if you open up this estimator and take its average, you have the mean of x times some factor, y minus its mean. And if you push this expectation inside by linearity of expectation, you'll just get mean of y minus mean of y here, and then those will cancel out. You'll just be left with the mean of x. We also have this property, which is that the estimator is orthogonal to any linear function ay plus b of the observation. Okay, so if you take the error and multiply it by a linear function and average it, you'll get 0. See the lecture notes for why this is true? This is an interesting property that we won't really use. One way you could use it is to argue to yourself that you need this property to hold. So you need the best linear estimator to have captured all the information, which means that there's nothing left in any other linear function. And then you can actually use this property to establish the LLSE formula. But we're not going to do that here. Instead, what we're going to do is just work out an example. So in this example, I'm going to give you a joint PDF of constant height over a particular range. So the height is 3/2. It lives between, so x lives between 0 and root y lives between 0 and 1, and we're going to draw this joint range as a sketch. Okay, so here's that curve, y equals x squared and y equals 1, and this purple one at x equals 0, and that's where we have to live. Okay, so from here, we want to know what is the MMSC estimator. And we know from the previous video that, and also this video, that that's just the conditional expectation. So we can work that out. So the conditional expectation in this case is just integrating the value of x times the conditional PDF given y, and I need to work out what that is. So we know that to get the conditional PDF, I just take the joint PDF divided by the marginal, in this case of y, and I need to get the marginal of y now. Okay, so I don't have that, but since I have the joint PDF, I can get it. I just integrate out x. So I integrate x out of the joint PDF. That means integrating this joint range from 0 to this curve, and that's where x hits root y. And if I plug that in, I just get basically 3/2 root y over y from 0 to 1 and 0 otherwise. Plugging all of that in, what we're going to get is just 3/2 divided by 3/2 root y, and that is over the joint range. Okay, so from x going from 0 to root y and y going from 0 to 1. Okay, we got the conditional PDF. Let's plug this in and see how it goes. So we have x 1 over root y dx, and we go from 0 to root y again. Now we have a half x squared from 0 to root y times 1 over root y. It ends up being root y over 2. So that's this halfway point. And if you thought about that before starting the integrals, this actually might have been what you intuited, because the conditional expectation should be the average value. So it should be about halfway. For any given value of y, it should be halfway from this line to the curve. And that's exactly what this root y over 2 curve gives us. And the reason we can expect to get that is because the joint PDF is of constant height. And so there's no values in the joint range that get preference over any other. We can also work out the mean squared error. It's a similar kind of calculation. Now we have to integrate over 2 variables instead of 1, but we're going to see the same kind of range bounds. So we have the MSE of the MMSC estimator. I know that's a lot to say. So we just average the error, so x minus the estimator squared. And so we integrate from 0 to 1 and 0 to root y. X minus root y over 2, that's the estimator, times 3/2, that's the joint PDF, dx dy. We end up with 1 over 20. I just worked that out offline. That's 0.05. What about a linear estimator? So what is the best possible linear estimator in this case? Well, we're going to use our formula. I'm going to choose this version of the formula where I have e of x plus the covariance of xy over the variance of y times y minus the mean of y. Okay, so the mean of x, I just get by integrating over the entire range, x times the joint PDF dx dy. To integrate over the whole range, I just integrate from 0 to 1 and 0 to y. And I'm going to see that pattern over and over again. So I actually have to get all of these values, the means. I have to get e of y squared. I do that by going, again, integrating over the whole range, but plugging in y squared. I have to get e of xy. I'm going to need that for the covariance. And I'm also going to need e of x squared. We'll get that in a moment. So I get all of these values, right, but from the computer, and I get the variance of y through this alternate variance formula. So e of y squared minus e of y whole thing squared. And so that's 3/7 minus 3/5 squared. That's 12 over 175. Again, you can work all of this out offline. The covariance of xy, I use the alternate formula, e of xy minus e of x times e of y. So that's going to be 1/4 times 3/8 times, or 1/4 minus 3/8 times 3/5, so 1 over 40. And then I can plug all of this together to get 3/8 plus 1/40 over 12 over 175. That's y minus 3/5. So I get 35 over 96y plus 5 over 32. So the exact numbers here are not important, but look at this line on the joint range. So I've plugged in the form of it in terms of x, in terms of y, and you can see that it does a really good job of approximating the nonlinear curve the Mmsc estimator gave. So it's the best line to approximate that curve. Okay, and you can see it's pretty close. So, maybe we'd be okay with that kind of estimator. And now let's just see, what is the mean squared error? So how much did we lose versus the optimal, which was 0.05? Okay, so I need to work that out. And I have a formula for doing that. So my formula, it says what I want to do is take the average of x minus the estimator, so the error squared, but I can just use this formula, variance of x minus the covariance of xy squared over the variance of y. And we have everything here we need except the variance of x. So the last term I need here is e of x squared to get the variance of x. And so I'm going to just work that out again, doing the double integral in exactly the same way before, but now using the x squared. I get 1/5. I use the alternate variance formula here. So I'm just going through all the details. It's a little bit tedious, but now we're almost done. So we get 1/5 minus 3/8 squared, and I get 19 over 320. And so if I plug all of this in, 19 over 320 minus 1 over 40 squared over 12 over 175, I get 193 over 3840. And this works out to be about 0.0503. Okay, so it's a little bit higher. In this case, we didn't lose too much by substituting in a linear estimator instead of a non-linear estimator. So to wrap up, what I want to talk about is that this estimator, the LLC estimator, is frequently used in practice with real data sets. And in that scenario, we usually call it something else. So we usually call it linear regression or simple linear regression because it's just a scalar case. That's what simple refers to. The data set we can think of as a bunch of pairs. So I have n pairs, x1, y1, x2, y2, xn, yn, right? And I have a scatter plot of those pairs on the right. And what I need to do to apply this estimator is to estimate the means, variances, and covariance from the data. So I'm going to do that. So the sample means I just average together the points that I have for x. I get a value for the mean of x. I average together the points of y. For this data set, I just have those values. Okay, nothing special. I just put them down. Sample variances, I do the same thing, except I average x minus its mean squared. And for y, I average y minus its mean squared. I'll say a little bit about this 1 over n minus 1 in just a second. The sample covariance, I do the same thing as the variances, except I have xi minus its mean times yi minus its mean. That's what I'm averaging. And then to get the sample correlation coefficient, I just put together the numbers I've already calculated. So just covariance over standard deviations multiplied together. So I get all these values and I can put them together to make a linear regression model. Okay, so I have x hat, which is mu hat plus covariance hat over sigma y hat squared, y minus its mean. And I can write that also in terms of the correlation coefficient. In this case, it's 0.66y minus 1.54. Okay, and I'm going to draw that line for you so you can see it. There it is. And we can see that it does a pretty good job of fitting the data. So that's maybe the line we would have drawn by hand if we wanted to find something that just passes right through the central axis or major axis of this data set. Okay, and finally, this 1 over n minus 1 factor, we're going to be seeing that again. The reason we use it here is it makes these sample variance and sample covariance estimators unbiased so that they, for any given value of n, their average is equal to the true value. We'll say more about that in a later video.